Welcome to Chapter 3, Section 3.4. Okay, Chapter 3 is about applications of differentiation. Section 3.4 is limits at infinity. Limits at infinity get you horizontal asymptotes. Let's see with an example. In this section, we let x become arbitrarily large, positive or negative. So large x values means you're going towards infinity. If you're going to the right, it is positive infinity. If you're going to the left, large values, then you're approaching negative infinity. Let's see what happens to y. For example, let's consider the function fx equals x squared minus 1 over x squared plus 1. If you put large values of x, either positive or negative, in this case it doesn't matter positive or negative because you are squaring both, you will get the same value, but you can make a table. Here is a table. X values 0, 1 or minus 1, 2 or minus 2, 3 or minus 3, and so on. 1000 or minus 1000. Look at the values. When x is 0, you get negative 1. When x is 1 or minus 1, you get 0. Plus or minus 2, 0.6, and so on. But look, when x is plus or minus 1000, we are not getting very large. Look at the numbers. It's minus 1, 0, 0.6, 0.8, 0.88 something, 0.92 something, 0.98 something, 0.999, 2 something, 0.9998, 0. You understand? This looks like as x approaches positive infinity or x approaches negative infinity, the curve in blue is approaching height 1 from both sides. All right. So what can we say? Limit x approaching positive infinity, you get 1. Okay. As x grows larger and larger, you see that the values of fx get closer and closer to 1. In fact, it seems that we make the values fx as close as we like to 1 by taking x sufficiently large. That's what it means to say limit x approaching positive infinity of your expression is 1. Okay, notice in here, as x approaches negative infinity, also you get 1. All right. So you could rewrite it as limit x approaching negative infinity, and the statement is still true. Okay. So which brings us to more formalism. We use the notation limit x approaching infinity of a function fx equals L to indicate that the values of fx approach L, that number L, as x becomes larger and larger. Okay. If this confuses you, remember your previous example. This is fx, this is L, and x approaching infinity. All right. X approaching infinity, fx equals L, means as x gets larger and larger, your value fx gets closer and closer to L. So, which brings us to the first intuitive definition of a limit at infinity. Let f be a function defined on some interval a to infinity. Okay, you want your function to be defined at some number a and all the way to the right. Then you say that limit x approaching infinity of fx is L. This means that the values of fx can be made arbitrarily close. Arbitrarily close means as close as you want to L by requiring x to be sufficiently large as you need. Okay. Here are some examples, right? So here is your function f in blue, and that is L. So f was doing whatever it was doing, it continues to do whatever, but after some point, it starts getting close to L. Okay, here is another example. This is probably something you're familiar with. This is exponential, right? So it's coming from some height and then going down, but not going down very much. At L, the height stabilizes. Okay. Here is yet another example. Your function is oscillating, but the amplitude is getting smaller and smaller, and you're approaching L. One thing many people mistake is that they think that horizontal asymptote is never touched. That is false. Here is an example. Your horizontal asymptote is the same L, y equals L, and your graph hits it infinitely many times. It just gets closer and closer. Or here it's hitting it once and then getting closer. Okay, it is not true that horizontal asymptote is not touched. In some cases, it never touches. For example, here, it has now never touched. In some cases, it touches very few times. In this case, only once it touched it. Okay, here, it crossed horizontal asymptote once and then never again. But here, it crosses your horizontal axis infinitely many times, and that's okay. All right. So another notation for limit x approaching infinity of fx equals L is fx approaches L as x approaches infinity. So this expression can be written in this fashion also. Okay. Continuing. Notice that there are many ways for the graph of f to approach the line y equals L. Y equals L is now your horizontal asymptote. Okay, as we look to the far right of each graph. Okay, now referring back to this picture, we see that for numerically large negative values of x also, the values of fx are close to 1. Oops. So by letting x decrease through negative values, without bound means without letting it stop, you let x keep going to the left, we can make fx get as close to L as possible. All right, 1 as possible. In this case, L is 1. So when you say y equals 1, you're talking about the line which has height 1 throughout, horizontal line. So this is expressed by writing limit x approaching negative infinity of x squared minus 1 over x squared plus 1 equals 1. As x approaches negative infinity, your expression gets closer and closer to 1. Notice the expression by itself is never 1, but the limit is 1. All right. So the general definition is as follows. Let f be a function defined on some interval negative infinity to a, then limit x approaching negative infinity of f of x is L. That means the values of fx can be made arbitrarily close to L by requiring x to be sufficiently large negative. So x is approaching negative infinity. So as x goes more and more and more negative, the value of fx gets closer and closer to L. Arbitrarily close means as close as you feel like. Okay. Here is your example. Here is a curve which on the right hand side goes wherever it wants to go. But on the left, as x approaches negative infinity, this curve seems to get closer and closer to L. Mind you, it could hit L, come back up, and so on, oscillate. But as long as it gets closer and closer to L, your limit is L. Here is another example. On the right hand side, your curve is below, but as x approaches negative infinity, your curve starts getting closer and closer to L, more and more close. So this is what it means to say limit x approaches negative infinity of f of x equals L. Definition. The line y equals L is called horizontal asymptote of the curve y equals fx if either of these happen. Okay, you want on the right hand side limit to be approaching L, or the left hand infinite limit also equal L. Okay, so this is important. Even if one of these happen, then the line y equals L is called horizontal asymptote. So to repeat, the line y equals L is called a horizontal asymptote of the curve y equals fx if either limit x approaching infinity fx is L, or limit x approaching negative infinity f of x is L. So here y equals L is a horizontal asymptote because the left hand limit all the way to negative infinity is L. Here also y equals L is a horizontal asymptote because as x approaches negative infinity, your curve approaches L. Okay, that was left infinity, negative infinity. Here are cases where the positive infinite limit is L. Positive infinite limit. Positive infinite limit is L. Okay, so I'll stop this video for now, continuing.